even though the machines that I use look like a cannon, but really what we are probing is taking a scalpel and locally tearing apart the atoms. Okay? And why I mean locally is because that pressure is there only for a short time, of the order of nanoseconds to a microsecond.
Welcome to It's a Material World, the show that uncovers why material science will change the world, with your hosts,
Praneeth Upadhyay
and Tom Miller. In today's episode, aluminum versus steel, the battle of alloys.
Hello, everyone. Our guest for today's show is Dr. Naresh Thadhani, professor and chair for the School of Materials Science and Engineering at Georgia Tech. He's been a member of the Georgia Tech faculty for the past 28 years, which is an impressive achievement on its own. So Dr. Thadhani is our resident metal expert for today, and his research focuses on the deformation mechanisms of materials under high-pressure shock compression. So welcome to the show, Dr. Thadhani.
Thank you, Puneet, and thank you, Thomas, for having me here.
Yeah, absolutely. We really appreciate you taking the time to be on our show and speak about this crazy world of material science and engineering that we live in. So our first question is, what inspired you to study and dedicate your career to material science and engineering, and in particular, this area of metallurgy?
So as Puneet said, that I've been at Georgia Tech for the past 28 years, and I have been in the overall discipline of material science and engineering, working since 1984. So it's quite a while. But I first started, just like every other kid who was thinking about a career path in engineering as a possible choice, but having no clue about what engineering meant. It turned out that I always was very fascinated with these metal structures, artworks. Having grown up in India, there's a lot of pottery that's made out of copper or brass or aluminum. And in many cases, it's mechanically formed or it's melted and cast into a particular shape. And I was always curious, how can a chunk of metal, which comes across as like a very hard thing, how can it be molded into this type of a shape? Now, mind you, I did not have any artistic touch, okay? So it was not from an artistic perspective. Okay? But it just amazed me that how can you turn this into a certain shape which has certain level of artistic complexity to it? And that's what impressed me. And somebody told me at that stage that this was the discipline of metallurgical engineering. And I said, okay, I have my answer. That's exactly what I want to study. Okay, and that's how I got into that discipline. Of course, metallurgical engineering now is part of material science and engineering. However, even at this stage of my career, I spend a lot of time working on all kinds of metals.
And so just for our audience and for us even, could you define this term metallurgy based on your experience in the field as well?
So if you think about it, metallurgy in essence is the study of the science and engineering of metals. What is again important to realize that there is a component of science. And what do we mean by science, right? Science is the discovery part. In discovering in the context of metals, it would apply to how does the metal have a specific structure? There's some kind of order in terms of the atomic arrangement. So how is that order created? And then based on that order, what properties does it have? So this linkage between the order, the structure, and the property, you can think about that's the scientific study, the science-based study. But then there is the engineering component of it. So I know there's a certain structure, I know there is a certain property, but what do I do with it? How can I use that to the benefit and make a material or device, a component that will leverage the properties that the material has? That's the engineering part. Now, there's also going backwards. In order to create a certain structure, what do? How do I extract that metal from wherever it comes from? Mostly metals come from their ore, the minerals. So the extraction part also involves engineering. So that's where, in essence, again, to answer your question, it's the metallurgy is the science in engineering of extracting metals, looking at how the structure evolves, how it's connected to the properties, and how can I make a device, a component that I can use it in any given application.
That's great. You really summarized the fundamentals of our entire MSc curriculum in just a couple minutes there, talking about processing, structure and composition and properties for the performance of the material. So I really did appreciate that. And so now I want to dive into two of the most common alloys that we use today. We see steel and aluminum alloys really present in a lot of different applications. So I was wondering if you could actually compare and contrast those properties, the microstructure and the composition of steels and aluminums.
Yeah, that's interesting. Aluminum and steel. Aluminum, a lightweight metal, density of about 2.7 grams per centimeter cube. And steel is almost 3 to 4 times heavier or denser than aluminum. Steel is very cheap in a way. Steel, if you go out and buy steel, the prices that will be quoted, of course, this is not small quantities. If you're talking about tonnages, it will be of the order of about 40 cents a pound. And it's available, obviously, in tonnages. And in fact, the most commonly used material today is still steel. There are a lot of other composites, polymers, and other metals also coming along, but definitely both in the context of the volume as well as the weight. Steel is the most commonly used material. Aluminum is expensive. It has its own benefits, but it's still expensive. I think aluminum may cost about $2 a pound or so. And it turns out aluminum is interesting that the price of aluminum fluctuates like crazy. More than 100 years ago, aluminum was probably $100,000 per pound. It was considered to be a precious metal. In fact, historically, Napoleon used to wear aluminum buttons on his jacket. So it was like a precious thing. It all stems from the way aluminum is made. Aluminum comes from bauxite, aluminum oxide, basically, and that has to be electrolytically separated into aluminum and oxygen. And that electrolytic process, obviously, it implies that it is going to require electrical energy. Electrical energy is not cheap. That's why it becomes an expensive process. And oftentimes, therefore, aluminum is recycled. The recycling of aluminum is very, very critical. Steel, on the other hand, is much more straightforward to make. Again, you're starting with the oxide of iron, which can be hematite or magnetite. You reduce it just by using fuel. It's actually an amazing process. The extraction of iron from its ore is literally an engineering marvel in terms of the way a blast furnace is designed. How does the ore come in contact with the fuel, the hot gases, and how does the separation happen? Again, these two materials, completely different properties. Steels also have the benefit in terms of, they're really called like engineered materials. In engineered materials, again, it's interesting that the term engineered is utilized to define these materials. And the reason being is that you can make a steel to have literally any kind of property. Steels have high strength, it can have high ductility, high formability, corrosion resistance, high temperature resistance. You can go in any extreme. Aluminums have some limitations.
It's funny that you mentioned the value of aluminum because someone who listens to our show, Beth, she actually gave us a fun fact that she shared with us because we put out to our audience that we were recording this episode that aluminum was once so valuable that they were going to choose it for the cap of the Washington Monument. So has a similar flavor to the Napoleon making buttons out of it as well. That's just kind of crazy. I know this is a little bit of a tangent, but I'm just curious, what was the inflection point there that made aluminum go from, you said it's still roughly 5 times the price of steel, but what was that inflection point that made it go from putting it on the caps of national monuments and putting it on the buttons of the most powerful people in the world at that time to being something that we drink soda out of? How did we get there?
You can relate it literally to the price of electric power generation. Even today, a year ago, 2 years ago, the price of aluminum fluctuates like crazy. And you can tie it to the fuel, coal, or oil that is used to power the electrical power plants that generate the energy. So there is literally a one-to-one correlation in terms of the price of aluminum. And the inflection point was at that stage when we had the capabilities to generate power at a reasonable cost.
So Dr. Thadhani, you mentioned that, aluminum can be recycled fairly easily. We've seen Novelis make a whole company from it and become successful. The world's largest aluminum recycler. So what's the comparison with steel? Can steel be recycled maybe to a similar extent or no?
Yes, steel is recycled also quite significantly. All your cars, all vehicles, at least the vehicles that were up until 20 years ago, I would say 90% of the vehicle was made out of some kind of ferrous alloy, primarily steel or some type of cast iron. And you've seen once you go to the junkyard, after you strip off the useful components, what do? They just crush that car and send it to the scrapyard, from where it just goes to the recycling part. The difference is that recycling steel and making steel from scratch, the price difference is not that significant relative to the recycling of aluminum versus making aluminum from scratch. Again, even in steels, if you want specialty steels, they're going to be exclusively made from recycled scrap material, and where again the recycled may be sorted out to make sure that is only a particular type. But in general, if you want a generic grade steel, the cost of recycled steel versus what you extract from the iron and use it, not very different.
Got it. So because the processing costs of aluminum are so much higher than steel, that's why it's so much more important for that recycling.
Exactly.
Continuing on with this comparison, delving into the impact a little bit, what has that impact been so far of the development of these lightweight metal alloy systems? And, why should customers and people who aren't material scientists care about lightweight alloys in their daily lives?
That's a very important part. Again, a lot of things are sort of connected to the consumption of fuel in everything we do. The use of gasoline for the miles per gallon that you have, whether it's a vehicle that is transporting passengers or an airplane, again, transporting passengers, or you think about trucks that are hauling goods. The cost of literally everything is tied to the fuel that is used to drive the transportation industry. So transportation industry is one major consumer of metallurgical product. And of course, the heavier the device, the heavier the vehicle, the greater will be the consumption of fuel. So that's where the challenge lies. What can we do to lightweight anything and everything that we drive, all kinds of vehicles? And interestingly, again, it's not just that aluminum is the best material or steel is the best material, or today's advanced composites are the best materials. It turns out that, just like human beings, these materials are also competing against each other. Okay. So there is a significant competition between aluminum and steel. And of course, polymers and composites on the other hand. So people try to make aluminum stronger and stronger so that it can withstand any type of dent that an automobile will see if you run against anything, or if there's some kind of an accident, it will dissipate all of that impact energy. So making aluminum stronger, it already has a low density, lightweight, but you want to make that as strong as you can. On the other hand, steel is heavy. So what do? You cannot remove density, right? Steel is already strong as well. But what you can do is go to lesser and lesser amount of steel. So automobile body, the metal that is used to make the auto body, can you use a thinner and thinner gauge of steel that has the same strength? And because of a thinner gauge, you are, by virtue of that, lightweighting the vehicle. But if it becomes too thin, then are you going to rupture it, to dent it in a way that it becomes an even greater catastrophic issue? So that's where the competing effects come in. And a lot of work is going on today whereby people are on the steel side. People are looking at thinner and thinner gauges of steel that have the strength, that have the rigidity. The rigidity is another aspect, the stiffness, because the thinner you make an object, the less rigid it's going to be, the less stiff it's going to be. Aluminum, on the other hand, you can sacrifice, you can go to thicker panels, but how much strength can you achieve? So that's where the balance comes in. And of course, cost becomes the underlying parameter as well.
And so in the sense that having the vessels that transport those things use less fuels will save consumers money essentially down the line.
Exactly. That's correct. Yeah, that's where the lightweighting is effective.
So, what are some of the challenges that material scientists are currently facing with that balance with potentially replacing steels with aluminums or other lightweight alloys in terms of strengthening?
Yeah, so it's interesting. There are various manners in which metals can be strengthened and goes back to the structure. So inherent structure itself has a certain inherent strength. But then when you have defects in the structure, defects can be problematic, but defects can also, if you design them appropriately, provides the enhanced strength effects. So that's the challenge, okay? And that's the scientific aspect, that's the engineering aspect as well. The science is how do I, or can I understand the role that defects play? And what are the different types of defects? Oftentimes we call them like point defects, line defects, planar defects, or volume defects. Each of these has a certain role. And if you look at something like aluminum can be strengthened by virtue of certain types of defect interactions. And those defect interactions are essentially, or in general cases, the line defects interacting with volume defects. We oftentimes in the literature call the line defects as something like dislocations, and the volume defects are like precipitates. So aluminum primarily strengthens by this precipitation strengthening effect. That's really the most dominant mechanism for strengthening aluminum alloys.
Just a quick thing there. When you say precipitates, just unpack that a little bit, or types of thing that looks like.
Good point. So what are precipitates? So any material, or any metal, any element, if you bring another element in contact with it, there is a possibility that there can be certain amount of solubility of component B in component A.
Right.
That certain amount of component B can dissolve into A. And that's what we are talking about. So it turns out that most metals will interact with one another such that there is a certain level of solubility under some condition. And you change those conditions, the solubility changes. And that's what leads to the solubility limit at a certain temperature. At high temperatures, generally the solubility is going to be higher. At lower temperatures, the solubility will decrease. And as the solubility decreases, then that other component will precipitate out and form a new compound or component or a phase in the matrix. And because it is a new compound, it is a volume, meaning it's a collection of atoms that are arranged in a certain configuration. And that's why we call it a volume defect. So that's what it is. Okay, so in aluminum, the dominant strengthening mechanism by virtue of this precipitation. Steels, on the other hand, are unique. They have multiple strengthening mechanisms. So the line defects can interact with point defects, they can interact with other line defects, they can interact with volume defects, they can even interact with planar defects. So in a way, yeah, they're complex, but if you think about it, if you imagine these interactions in the form of like dials, knobs, so you can dial it, the type of dominant mechanism you want without creating defects that would have undue effects on the material response. So that's basically on a structural scale, what we're getting to is aluminum, because it has more or less a singular dominant mechanism. The next in aluminum is to try and identify other possible mechanisms. So can I change the chemistry? Can I add other elements in aluminum which will bring about other mechanisms which I can use to strengthen aluminum? Because steels, you don't have to worry. There are so many different mechanisms. Turns out, one can utilize these various mechanisms in steel. You can make steel that is actually softer than aluminum or even stronger than many of the ceramics. So the range of properties that you have is amazing.
Speaking to that example, we had talked ahead of the episode about this historical context of steels coming in samurai swords in pre-industrial Japan. How did that end up working out? Because that was before we had this modern understanding of metallurgy.
So the samurai sword, one of the ways it is done is, again, taking literally a strip of steel, mechanically rolling it or passing it through a set of rolls, folding it, rolling it again, folding it, rolling it again. And you go through this multiple times. So the repeated deformation it has is what ends up in refining that grain structure, as well as creating more and more of these line defects, which end up giving you the high strength. Now, you can ask the question, well, why can't we do this in aluminum? And that's something that people are actually looking at. In aluminum, interestingly, it turns out that one might imagine that aluminum is a lot softer. So from that perspective, so mechanically, aluminum should be more formable, but actually not. Aluminum doesn't have the ability to stretch as much as many of the steels do. The limit of how much you can stretch aluminum is actually lower than many of the iron-based alloys. So the same thing now, if you think about, if I take a plate of aluminum, and if I want to make a samurai sword out of it, I can do 1 pass, 2 passes, 3 passes, maybe 10 passes. But then, if I try to do more, aluminum will start shattering. I will not be able to go through multiple passes. It has a limit unless I add some other elemental additive.
So I have a quick question about that. How I'm thinking about just aluminum that's around us, and the first thing that came to mind was aluminum foil. How is that formed? Because that's such a thin piece of material. How does that process work?
That's correct. Again, aluminum foil also turns out that it is generally 98.5 to 99% purity. It doesn't have any other alloying additive, maybe some amount of oxygen present in it as an impurity. Mm-hmm. And actually, the more oxygen there is in it, stronger it will be. You don't want it to be too strong to be able to make that foil. Generally, it will be made by a continuous casting process where you melt aluminum and then continuously cast it in the form of a slab. And that slab then goes through repeated reductions in a rolling mill, but not large reductions. So there's going to be almost like a continuous process where the reduction takes place in smaller and smaller levels. First, at elevated temperatures to try and get greater amounts of reductions. But later on, when you reach the thin foil state, you're going to be doing cold rolling to get that thin foil, which is typically, I think, of the order of 25, 50 microns in size. The repeated reduction that allows you to reach that scale rather than a single reduction.
And so talked a lot about these alloys and steels out in the industry, but let's talk about you a little bit more. So there's a little bit of an elephant in the room that we have yet to address, or more appropriately, there's a little bit of a cannon in the room. So for your research, you look to study the rapid deformation of materials under high velocities, particularly the study of materials' response to extreme conditions, which involves the use of a research grade cannon. And why is studying the material response of interest to materials scientists and engineers under such extreme conditions? And in particular, how does this play into developing this next generation of lightweight alloys or even ferrous alloys?
Yeah. So the field of metallurgy is the study of science and engineering, right, of metals. So to study the scientific part, let's talk more on the science side. So if you want to understand the science, we want to look at how does a metal respond to any type of stimuli that it is subjected to. Now, the stimuli can be temperature, it can be stress, it can be a chemical environment, it can be anything. So what I use is stress or high pressure. So what happens, or how do metals respond to high pressure? And not just high pressure, but high pressure that is present for a very, very short time. So by reducing the time scale across which the pressure is applied, you can imagine that you are literally going into probing the atomic level of happenings in the material. You're taking a scalpel, even though the machines that I use look like a cannon. But really what we are probing is taking a scalpel and locally tearing apart the atoms. Okay. And why I mean locally is because that pressure is there only for a short time, of the order of nanoseconds to a microsecond. So it's only a certain scale of that metal that is going to be subjected to that condition. So now, imagine. So rather than looking at the big block of metal, I'm probing locally. And that local probing opens up, literally, I'm going the raw state of the metal. And what I'm interested in researching is how do materials undergo physical changes? There's a change in structure from one state to another state. Is that structure going to be stable? Or if I remove the pressure, will it go back? So that's the physical change I'm interested in. I'm also interested in the chemical change. It turns out that under these extreme conditions, there can be chemistry. Two components can react with one another. In fact, if you look, around us, so diamond in nature, diamond is an allotropic form of carbon. And a lot of diamond that you have that is natural diamond in the Earth's crust is believed to have been formed when you had the earthquakes or when you had a meteorite impact and the carbon turned into diamond. And it's been preserved as diamond in certain places. It also turns out, if you look at some places where there's a meteor crater, like Flagstaff, Arizona, turns out that in some of the areas there, the iron from the Earth's crust reacted with the nickel from the meteorite to create a new compound of iron and nickel. So there's a chemical reaction, there's a chemistry that is taking place. Now, imagine, meteorite impact was a very, very severe condition. Okay, but I'm interested in exploring new chemistries as well. I cannot wait for meteorites to fall, so we have to have our own.
Yeah, you're putting your career too much on the line on meteorites if you're doing that, so I get it.
So that's what you're studying, is the high-speed impacts of meteorites.
But it's not the same scale either.
Right.
That's the interest. How does that chemistry take place?
Right.
Realizing that two components are sort of getting together to form a new compound in like nanoseconds or microseconds. So what's the mechanism? Under heat, we can imagine, right? If you're just heating the material, you can say nickel maybe diffusing into iron or iron diffusing into nickel, creating a bond, and everybody's happy. The nickel is happy, iron is happy, and they created a new compound. There's not enough time for diffusion to take place if you're talking about just 1 microsecond. But you're bringing nickel and iron atoms in like the nascent form. You're cleaning the surfaces. So how is that chemistry happening? That's the interesting point. So physical change, chemical change, and of course, mechanical changes. The mechanical changes are simply how does a material deform, can lose its strength, and eventually how does it fail? Obviously, there are a lot of scenarios. If you talk about automotive crash, if you're talking about meteorite impact, if you're talking about space debris that is colliding, we have the astronauts now that just landed on the space station just day before yesterday they went. Imagine the protection systems that the space station has. We need to be cognizant. We need to have the science and technology that is necessary to make sure that the space station is going to be safe and it's going to withstand any type of meteorite debris. So the understanding of the mechanical behavior of these materials under these extreme conditions becomes very important as well.
That's really cool. We actually have a question that's inspired by one of our listeners, Rohit. If you follow us on Instagram at It's a Material World Podcast, you can get involved with us and be able to ask questions that we'll forward along to our guests. So really cool opportunity there. But Rohit had a really cool question for you, and he was wondering, what are some of the current knowledge gaps that material scientists have in terms of understanding the strengthening and processing of steels and aluminums, especially because we've, as a research community, looked into steels and aluminum so much over the years?
The limitations or the challenges, if you will, Jem, you can think about maybe two areas, two aspects. You cannot just discover your way out to new materials. And every time you have some challenge, you cannot say, well, let me discover a new material, or I'm going to use this new material, so let me get back to the drawing board and discover. You cannot do that. The other side of it is also, we have a lot of existing cool materials that we use in everyday life. And look around us. It's amazing, the materials that we have today. I think across the board, no matter what technology you look at, whether it's in the information technology, the transportation industry, the energy industry, the medical industry, the successes of all of those technologies are thanks to materials, okay, the innovations in materials, right? I mean, if you did not have the ability to make silicon the way it is made today, forget about your iPhone or laptop or any of the devices that you have today. So I think the question then goes back to how far can I go? Or how much can I extend the limits of performance of an existing material? If I'm going to use a certain material, metal alloy, for a turbine blade application that's going to power an engine, right now we are still very conservative, okay, meaning we don't want to push the limits. And the reason is because we don't have confidence in the data that we have collected in terms of what are the properties of those materials. Because there's always a variation in, if you make 10 pieces of these turbine blades, they're all going to have different values of the strength or whatever property you need. So in a design criteria, you're going to consider the lowest value. But then that means you're sacrificing a lot. Can I come towards the other direction? So that's what I mean by stretching the limits of material performance. How do you do that? The same thing translates to discovering new materials. As I said, you cannot just discover your way out. But the challenges there are, by the time you discover a material in a lab and use it in an actual application, depending on the application you're looking at, it can take like 10 years or 20 years. So by the time you discover a material, the next generation will come and use it. We cannot afford that. So what both of these aspects call for is accelerating that pace. That I can make, that Thomas, you put it here, when you are working on the next generation of materials that is needed for the space station or the airplane, you will have the ability to, with confidence say that, yeah, go ahead and use it to this limit. You can stretch this to this limit. Or you will have the confidence to say, forget it, we don't have the material, but I can get you that material in 1 year.
We've talked about what's going on in steel and aluminum research right now, and we really want to dive into the future of it. And so I wanted to ask you, where do you see the lightweighting of metal products progressing in the next 10 to 15 years? Do you think we're in a post-steel era moving forward in certain parts of the industry that previously leaned heavily on the use of steel alloys, maybe the automotive industry, or what are your thoughts on this?
No.
Also, of note, before you answer, you did noticeably shake your head when we said post-steel era, so on the record. but we'll let you respond.
Yeah, so I'm biased by steel, so I think that was the reason.
It was a hard no.
But remember what I said, just like human beings, materials compete against each other. So the moment you discover a new aluminum alloy that is going to compete with steel, I'm sure you will see steel researchers come up with advanced high-strength steels. We are in I think what people call the third generation, or maybe it's the fourth generation of advanced high-strength steels. Maybe these generations will continue and you'll come up with the fifth and the sixth and the seventh generation of steels. What does that mean? Ultimately with steels, you have the high strength ability. That you have the high stiffness. It's the density. So you can play around with the density by introducing elements that will lower the density and still give you the same type of properties. So that's one avenue. Or still continue to work on creating microstructures or creating those cell structures, the grain structures that give you those beneficial properties. Even if you have to go with steel that is literally a foil, that will be amazing, right? If you think about your car body, it's like a foil. You can maybe poke your finger into it, but without rupturing it.
That would be scary if I could.
Yes, but then you will need stiffeners. But there is another way to do it. I think that's what will happen. So the body will no longer be just a thin sheet, but it may be a package with stiffeners, just like the wings of an airplane. The airplane wing is not just a hollow structure made out of titanium, but it has stiffeners. So maybe something like that might be a possibility with steel. On the other hand, with aluminum, by all means, I think new chemistries are being looked at. Now, aluminum is also facing competition with magnesium. Magnesium and magnesium alloys are actually half the density of aluminum.
That's convenient.
So magnesium is coming up too. A lot of work going on in magnesium. Trouble with magnesium is that you cannot, at least today, very easily mechanically form it at room temperature. All of the forming of magnesium is done at high temperature. So any type of cold working that you would have to do to create a thin sheet, that's a problem. Ultimately, I think to answer your question, these developments are going to move forward competitively. On the one hand, steel competing with its newer properties, aluminum, and obviously on the other side, the composites are becoming more and more popular. Also, cost of doing all this thing is probably going to override every other factor.
But, at the end of the day, hopefully this competition, like you said, will help continue to drive this innovation forward, right? And get those processes expedited. So
and we'll keep people like me busy working.
Yes. Yes, keep you busy waiting for your meteorites, exactly. And of course, keeping the cannon operational. So, how much impact do you envision the data analytics, the computational material science and engineering having in the fields in the future? And what would be your recommendation to material science and engineering students and professionals about the utility of taking a serious look at computational science as something in their skill set?
Yes, I think computations are going to be an important skill set for every material scientist, engineer. No matter you decide to go into an industry-based career or a research career, I think it's just going to become a routine skill set that everybody is going to need to have. And I will say that it's not a difficult thing. It's not something that should scare people. But I think when you look at the value of it, when it gives you the realization that rather than doing 10 experiments in the lab where I have to work day and night to prepare my material and do a test, and at the end of the day, I may or may not get a clear result. Something may happen in the test. When you do something, there are errors. And oftentimes, it becomes challenging as to how do I separate the actual result from the error, whether the error is related to the sample that I prepared or the machine misbehaving and giving an error because of the hydraulics did not work properly, because of the oil or the pressure gauge did not give you the correct effect. So testing is time consuming. It's an iterative process, and there are always errors associated with that. Computational models are not free from those things either. Computations rely on actual models, and models need to be validated with data. So if you don't have the data, then oftentimes people use this phrase, garbage in, garbage out. So having an understanding of what you are putting in the computational program, how you're using it, and what you're expecting it to give you, and then how are you going to utilize that information? I think all of those aspects are necessary. Now, it turns out this realization of the importance of computations, we have known this for more than 20, 30 years. But because of these limitations, again, I think today we are at that stage that our measurements are becoming more and more reliable, which means that we can use these computational models more reliably, have better validation. Our understanding of the science is improving. The computational power is increasing. The speed at which you can run these calculations, my God, it's phenomenal. So think about the process of rolling, or melting, or additive manufacturing, any of these processes. Imagine if you had a feedback loop where you are, as the process is happening, you're measuring the structure, you're monitoring the structure, but you're also measuring the properties in real time. And all of that data is fed into the computer, which is then responding by tweaking the knobs of the processing system. So if something is happening too fast, or too slow, or the temperature in a certain area, maybe for whatever reason, exceeded a certain limit, It will bring it down to where it is needed. So if you can do this in some kind of a high throughput manner, that's the holy grail. I think that's where we are going. And it's not just in terms of making the material, but now apply it to the usage of the material. Now, you think about bridges. People use all kinds of sensors that are placed on the bridge. So every time you're driving across the bridge, the sensor is monitoring. Now, imagine that same sensor actually placed on the metal itself. Or imagine it in a different way. You're not embedding, you're not gluing or strapping a sensor, but the material itself has a built-in sensor, meaning the atoms themselves are configured in a way that they're able to sense the changes that are happening in that metal. Nature does it, right? Nature does. I mean, how do living species know that it's getting cold? How do the birds know the direction they need to fly?
Right. The response to stimuli is the, programming our materials to respond in the same ways.
Exactly. Whether it's the wings, the feathers, the fibers in the feather, or the fibers that are the hair on the skin, all of those are sensors. And those sensors are what sense the stimuli, the temperature, the air pressure, or whatever it is, and then send a signal to the brain, and the brain then responds and says, okay, go in this direction.
Yeah,
so
cool.
Can we build materials? I think that is the challenge. Right? Can we create materials? And I think to do that, you need this integration of computational power, the ability to do the measurements. Because again, imagine, okay, you have a sensor mounted on a metal. It will give you some signal, but you need to understand what the signal means.
Right.
To understand that signal, you need the computational capability.
It reminds me of smart materials too. That's so cool how it responds to stimuli and can change on its own without any external acting upon it to make those changes. So that's super cool.
Yeah. And metals have that ability, right? I mean, you talk about smart metals, smart alloys. I mean, there's this class of the shape memory alloys.
Nitinol.
Right?
Which is an alloy of nickel and titanium.
So nitinol is considered a smart material. Well, it's not smart in the sense that it has a brain or anything like that. Just its ability to go through changes in structure based on the stimuli that it sees.
I was just actually writing a paper about nitinol, and it's really cool how it has that shape memory property and super elasticity. So you can bend it, you can stretch it, and it'll retain that shape. But then the second you put it under a critical temperature, it'll actually remember its original form and return to that form too. So super cool how these materials work. And so just moving on to something you mentioned previously about our current instrumentation limitations that we're facing. The sample that we conduct a test on is inherently different from the sample that we analyze through a microscope, either post-mortem or just a different sample altogether, maybe slight differences in that microstructure. So that means that we can't do structure characterization and property measurement in situ or during the process of that sample testing, at least not yet. So in your opinion, if we were able to develop instrumentation to accomplish this, how would that benefit the material science field? Can you elaborate on that?
Yes, we are getting to that stage where, at least in some scenarios, we are able to do that. Like the example that I gave you about this nickel reacting with iron to do this chemistry. And I do a lot of this chemistry type of work even in my lab. And I have to rely on doing the experiment and then taking that material, putting it in whatever instruments we have available for determining the structure. The instrument will show diffraction peaks or X-ray or whatever. Or if I can go to the scanning microscope and see there is some degree of mixing between the components, and I'll say, hooray, I got some chemistry here. But how did that chemistry take place? What was the driving force? Did the nickel diffuse? Did the iron diffuse? I have no clue in terms of what is the science that is happening that's leading to that chemistry. Now, why is that important? Well, if I don't know the science, I will not be able to design the process to yield the product that I want. I will have to just rely on trial and error. I will have to do multiple experiments and say, okay, if I do the experiment like this is what will happen. But imagine if I could put the Canon inside the transmission electron microscope. Nobody will let me do that. Or the other way around. Or bottom line is, if I bring my stimuli Doesn't matter whatever the stimuli is. The stimulus can be heat. The stimulus can be electrical field. The stimulus can be chemical environment. The stimulus can be a pressure pulse that is generated by a laser beam. Those are possible. I can bring those stimuli inside the microscope. And with my eyes, I can see as the stimuli is applied to the metal, how are the atoms responding to it? And if I can see that, I can see the atom motion. Is it the iron atoms moving, the nickel atoms moving? Are the barriers being created? What is driving that phenomena? Then I get a clear understanding. I get the exact science of what is happening. Then I can tune it to make the material I want. Or if I'm interested in the failure of the material, I can see where did the crack initiate? And that's what one of our faculty members, Josh Catcher, that's what he's doing. He has the ability to pull a thin strip or wire of a metal inside the electron microscope and see how are the atoms stretching until you get the onset of failure. So if I know that, now, if needed, I can prevent that by utilizing some tricks, the scientific, the alchemy or whatever I want to use. Or if I want to take advantage of that, then I can see, okay, what do I need to do to accelerate that process? We have also faculty that are looking at the electrical environment, the chemical environment. If you're talking about batteries, the degradation of batteries. So if I have a material through which I'm sending an electric current, while the material is in some kind of an electrolytic environment, I want to make sure that while there is a flow of current happening and there is a chemical environment, is there any type of degradation going on? So if I know it at that scale, I can decide what to do to prevent it before I actually make the battery, and then battery is used in a certain application. And then we find out that there was a fire in an airplane, and it came from the battery that was part of, your computer or whatever the device was.
And so we've really covered a lot about this field of metallurgy, material science, and engineering in particular. So I'd like you to bottom line it for us. There are 3 some odd things that our listeners should take away from this conversation. What would those 3 things be?
The first thing, and of course, I'm going to brag about this. I think material science and engineering is a fascinating discipline. There's this combination of science, there's a combination of engineering. There's room for somebody who wants to strive to be a scientist, all the way to somebody who wants to solve problems or be an entrepreneur and really create new things. Okay, there's room for everyone. That's number one. Number 2 is that I think we realize that there is no magic material. There's no magic material that can do everything. So there is a significant room there to come up with some materials that can have those specific needs. Or what we may have to do is create what are called like hierarchical materials. It may be just aluminum, but can I change aluminum in a way that the interior to the exterior is different? Or one edge to the other edge, or one surface to the other surface is different. And there is a certain hierarchy of the structure as you go through that thickness or that span, or the different parts of that material. So you're still working on the same material, but you are changing the hierarchy. It's just like a bone. There's a lot that we can learn from nature. Bone, whether it's human or animal bones, they are not a monolith. They have a hierarchical structure. And that hierarchical structure provides that strength, that provides the corrosion resistance, that provides the stiffness, the multiplicity of the properties. So that would be number 2. The third thing I would say is that we can no longer afford to have materials that have only a singular function. We need to be thinking about materials that are multifunctional, that have multiple functionalities. So as I said, if you have a rod of a material that is used as a rebar or something, make sure that that rebar also has embedded sensors that are part of that material, not something that are attached to it, but just inherently part of that material. So
the smart materials.
So having those multiple functionalities, or a material that can be strong, that can also be resistant to heat, can be also resistant to chemicals, electric fields, everything. Okay, and can change color as well.
Sure, why not?
So,
Yeah.
Dr. Thadhani, you are a fountain of knowledge. And so if anybody else wants to reach out to you and, have this conversation with you, what is the best way to reach you?
Yeah, absolutely. I think the best way to reach me is through my email. I think on our website, you'll be able to see my email. And I look at my email very regularly, and I'll do my best to respond as fast as I can. But yeah, I'm open to any type of conversation from prospective students, from anyone in the community. I'm excited about our discipline, and I hope I can, share that excitement with everyone and make it a contagious thing, unlike some other contagious things.
Yes, we'll trade COVID-19 for the contagion of material science any day.
Yes, that's correct.
Thank you for being part of the show. We really appreciate your time and for sharing all of your insights about this field that Puneeth and I have really come to adore.
Thank you for having me. Thank you for giving me the opportunity, and I really, really appreciate you all doing this. This is wonderful.
Thank you for tuning in to this episode of the It's a Material World podcast. We look forward to releasing our next episode in 2 weeks. Please subscribe to our podcast feed in your favorite podcast app so that you never miss an episode. And tell your friends about our show on social media. But until then, if you want to hear from us, we are on LinkedIn, Twitter, YouTube, and Instagram. Follow or subscribe to us on those platforms to keep up to date with all things It's Material Worlds between our episodes. Links to our social media sites will also be in the show notes. If you have any feedback, we'd love to hear it. We're just 2 college students just getting started out with a podcast, and we really want to grow this show with our community's input. You can send us feedback through messaging on any of our social media sites. We also love to hear your comments through reviews on Apple Podcasts. Feel free to also provide feedback by messaging us directly on LinkedIn, either to Puneeth Upadhyay or Thomas Miller. But until then, take care and stay healthy.